This video is about solving exponential equations and logarithms. Here you see two examples of exponential equations. As you can see, these are called exponential equations because, first of all, these are equations. You can see the equality sign, and the unknown x appears in the exponent. So that's the reason we call these exponential equations. The same thing in this other one. You can see that you have an equality and the x, the unknown, appears in the exponent. So for that reason we call these exponential equations. In order to solve an exponential equation, sometimes you need a concept called logarithm and sometimes you don't. So for these two examples, you don't need logarithms. The only thing you need to do for these kind of equations is that you need to have the same base on both sides, and if they have the same base on both sides, then in order to solve the equality, the two exponents have to be equal. So for example, here 5 to the power of x equals 125. 125 is 5 to the power of 3. Okay, and that means that x is 3, because if we have an equality and the bases are the same, then for the equality to hold, the exponents have to be the same. Let's look at this other one. We have 10 to the power of 2x minus 1 equals 0.001, but 0.001 is the same as 1 over 1,000. 1 over 1,000, and 1 over 1,000 equals 1 over 10 to the power of 3, which is 10 to the power of negative 3. So now we have the same base 10 on this side and base 10 on the other side, and for the equality to hold, the two exponents have to be the same. So we form this equality: 2x minus 1 equals negative 3, and we solve it. This implies that 2x is negative 3 plus 1, so 2x equals negative 2, so x is negative 1. Let's look at another example of an exponential equation that can be solved without a logarithm. 3 x squared plus 1 equals 27. Okay, you should notice that just like the previous two examples, you do not have the same base, but you have to introduce it. 3 to the power of x squared plus 1 equals 27 is just 3 to the power of 3. So now you have the same base, 3, on both sides. So in order for equality to hold, x squared plus 1 has to be equal 3. That means x squared is 2. At this point you can use the square root property. This implies that x is plus or minus radical 2. Okay, one last example of this kind of exponential equations. 4 to the power of 3x minus 2 equals 32. For this one, you will have to change the exponent on both sides. You should actually notice that 4 is 2 to the power of 2 and 32 is 2 to the power of 5, and use this fact. So I'm gonna write 2 to the power of 2 instead of 4. That raised to the power of 3x minus 2 equals 2 to the power of 5, that is 32. Then simplify this. If I have something to a power and that whole expression raised to a power, I have to multiply the two exponents. So on this side I get 2 to the power of 6x minus 4 equals 2 to the power of 5. Now I have the same exponent, the same base on both sides, and for equality to hold, the two exponents have to be the same. So this implies that 6x minus 4 equals 5. So 6x equals 9 and x equals 9 over 6, which is 3 over 2. So these were some exponential equations that you're able to solve without logarithm. I think I'll give you some more examples of that. 10 to the power of 2x minus 1 equals this one I already did. Yeah, 3 to the power of x equals 81. You should notice that 81 is 3 to the power of 4. So this is 3 to the power of x equals 3 to the power of 4. This implies that x is 4. And 5 to the power of 2x plus 1 equals radical 5. You should notice that 5 to the power of radical 1, radical 5 is 5 to the power of 1 over 2. So this is 5 to the power of 2x plus 1 equals 5 to the power of 1 over 2. So 2x plus 1 equals 1 over 2. So 2x equals, moving the 1 to the other side, negative 1 over 2. This implies that x is negative 1 over 4. Just need to divide both sides by 4, by 2. Okay, so this is the technique you use when you're solving an equation, an exponential equation, and you don't need to use the logarithm. But what are the logarithm? Because for some of these equations you need this concept. So logarithm is just a new notation. It's not a new concept. So as you can express the square root of 2 as 2 to the power of 1 over 2 and radical 2, there are two ways in order to express that. For example, 2 to power of 3 equals 8. That's one way of expressing that the raising 2 to power of 3 is 8, and the other notation is log 8 base 2 is 3. So as you can see, logarithms are just a new notation in the context of exponential expressions. So these two are equivalent. 2 to power of 3 equals 8 can also be expressed as logarithm of 8 base 2 is 3. So for example, generally, logarithm of y base b equals x if and only if b to power of x is y. So the way I memorize that is logarithm y base b equals x. I just have these two arrows in my mind. This means b to power of x is y. B to power of x is y. This is equivalent to that. So for example, logarithm of 10,000 base 10. What is this? You are asking yourself, what is the power such that I need to raise 10 to that power to get 10,000, and that power is 4, because 10 to power of 4 is 10,000. Logarithm of x base 4 is 5, and you want to know what x is. So x is the number that you get by raising 4 to power of 5. So this can be written as 4 to power of 5 is x, which means that x is 625. Another example, logarithm of 1 base x is 1. Now want to find the base. So again, this is the same as x to power of 1 is 7. X to power of 1 is 7. So x to power of 1 equals 7 to power of 1. X has to be 7. Logarithm of 81 base 3. So you're asking yourself, 3 equals x. You want to solve this. You're asking yourself, 3 to power of what power is 81? And that power is 4. Logarithm of 1 over 2 base 2, and you want to solve this. So you're asking yourself, 2 to what power is 1 over 2? But 1 over 2 is 2 to power of negative 1. Okay, so x is -1. There are two bases that are more important than the other ones. One is base 10, so logarithm of x base 10, which is called the common base. So base 10 is called the common base, and it is usually omitted because it is implied. So if I just say log x without putting the base there, I mean base 10. The other base that is important is e. So log x base e, where e is an irrational number which is about 2.718. And this is also has lots of applications in science and engineering. Whenever you have base e as the base of the logarithm, you change the notation to ln. So lnx. So if I have lnx, I know that the base is e. If I have log x without the base, I know that the base is 10. For example, log 0.01. I know the base is 10 equals x. I'm going to find what x is. I know the base is 10, so this is the same as 10 to what power equals 0.01. And since 0.01 is the same as 1 over 100, this is 1 over 10 to the power of 2, this is 10 to the power of -2. Okay, now I know that I have the same base, so x is -2. What is ln e? So here I know that because I'm using ln, the base is e, so this is the same as asking e to what power is e, and the answer is 1. E to power of 1 is e. Okay, now let's take a look at some properties of logarithm. The first property is log a base a is 1. The reason is that this is the same as a to power of 1 is a. Yes, a, think about those arrows, a to power of 1 is a, which is something obvious. The other one, logarithm of 1 in any base is 0. So log 1, doesn't matter what the base is 0. Why is that? Because this is equivalent to a to power of 0 is 1. And this is part of the definition of exponents. Any non-zero number to power of 0 is 1, and this is its equivalent in the notation of logarithms. Logarithm of 1 is 0. The other property is logarithm of a to power of x base a is x. And why is that? Because this becomes equivalent to a to power of x is a to power of x, which is obvious. A to power of x is a to power of x. Okay, I see here I have some problem. I'm going to rewrite that. Log a to power of x base a is x. Why does this equality hold? Because it is equivalent to me saying a to power of x is a to power of x, which is obvious. Another way of looking at this is, here I'm asking what is the power that I raise a to that power to get what is the power that I raise a to that power to get a to power of x, and that power is x. For example, log 5 base 5 is 1, because 5 to power of 1 is 5. Log 1 base 7 is 0, because 7 to power of 0 is 1. Log 2 to power of 3 base 2. Log 2 to power of 3 base 2 is just 3, because 2 to power of 3 is 2 to power of 3. Another rule about logarithm is the one that is used for change of base. Most scientific calculators can calculate logarithms of base 10 and logarithm of base e. But what if you want to calculate something like this? Log 5 base 7. Your calculator does not have the base 7, so how can you calculate log 5 base 7? The property you're going to use is called the change of base. The change of base says logarithm of a base b equals logarithm of a base c over logarithm of b base c. So you can use any arbitrary number as the base, and this equation always works. For example, logarithm of 5 base 7 equals logarithm of 5 base 2 over logarithm of 7 base 2. But you see that this one does not solve our problem because the calculator does not give us the logarithm of base 2 as well. But you can also say this equals logarithm of 5 base 10 over logarithm of 7 base 10. Now you can use your calculator to find logarithm of 5 base 10 and divide that by the logarithm of 7 base 10 to get this calculated. You could also use ln. For example, logarithm of 11 base 3. This is the same as ln 11 over ln 3, and you can use your calculator to figure out what ln 11 is. You divide that by ln 3 and you have this calculated. Okay, so let's look at some one example in which you need to do that. 3 to power of x minus 1 equals 5. This is the same as me saying log 5 base 3 is x minus 1. Yes, because again, think about the arrows. 3 to power of x minus 1 is 5. 3 to power of x minus 1 is 5. The same thing as this one. So this implies that x is log 5 base 3 plus 1. But log 5 base 3, the calculator does not give it to you. You need to use the change of base. So this equals x equals, we can use ln 5 over ln 3 plus 1, and now we can use our calculator to find that this is about 2.465. Okay, and that's it for solving exponential equations and logarithm.